So, we would start with turbulent flow in this class. Before we start the turbulent flow, the treatment of turbulent flow, which as I mentioned before is quite complicated, I would start with something very simple. Let us think of fully developed flow in a horizontal pipe. So, whenever you have a flow in a horizontal pipe, and if we consider steady state, and since it is horizontal, there is no effect of body forces. So, what the flow only takes place as a result of applied pressure gradient. So, if you apply pressure, the fluid starts to flow, but in order when it attains a steady state condition, that means the velocity at any specific location is not a function of time, then this pressure gradient must be balanced by an opposing force, and the opposing force is provided by the friction of the fluid. So, if one writes the Navier-Stokes equation, the z component, the axial component of the Navier-Stokes equation in a cylindrical coordinate system for steady flow, steady fully developed flow in a horizontal pipe, the form of that equation would look something like this, where all the convective terms are going to be 0. This is del P del Z with a minus sign, and since it is cylindrical system, this denotes the viscous forces acting on it. So, this is the gradient of pressure, the pressure gradient which is forcing the fluid to flow, and this is the shear stress which is opposing the motion of the fluid. So, at steady state fully developed condition, this would be the equation for the z component of equation of motion. So, one would be able to integrate this equation and to obtain a constant of integration as c, and we all know that at r equals 0, that at the center line the shear stress must be equal to 0. So, if the shear stress is 0 at the center line, that is at r equals 0, center line of the pipe at r equals 0, we should give us the integration constant to be equal to 0. So, the expression for shear stress in a flowing fluid would simply be equal to r by 2, where r is the radial distance coordinate and del P del Z is the pressure gradient in the which is forcing the liquid to move from lower values of Z towards higher values of Z. This is the shear stress on the fluid. So, when I express it in terms of the wall shear stress, that is the force experienced by the solid wall in contact with the fluid, then tau W would be simply equal to minus tau R Z, but the location here is at the wall, at which point the R is going to be equal to capital R, where capital R is the radius of the pipe. So, substituting the value of R in here, one can obtain the wall shear stress to be equal to minus R by 2 del P del Z. So, this is valid both for laminar and turbulent flow. We will use this later on in our discussion. But let us come to this part of the turbulent flow. What I have drawn over here is the instantaneous velocity, which is denoted by Vz. So, this is the axial value of velocity at any given location as a function of time. So far in laminar flow, we used to get only one value of velocity, that is the velocity is a constant, and therefore, it will not fluctuate. But in turbulent flow, where there is going to be a lot of intermixing, the exchange of eddies, the formation and exchange of eddies and so on, and if you are measuring the velocity of the fluid at a given point, the velocity is never going to be a constant. It will be an arbitrarily oscillating function of time. So, at one point instant of time, the velocity could be high, at the next instant it could be low. So, it would arbitrarily oscillate as a function of time. Now, if you integrate this over entire time, if you find a time average of this velocity, where the averaging is done over a time scale which is large enough in comparison to the time scale of oscillation. So, if it is oscillating like this, you are averaging over a large time. and therefore, the value you would thus obtain would be a constant. It would be independent of oscillation, and this is called the time smoothed velocity. So, if you can integrate the fluctuating velocity over a large time domain, then the constant value that you are going to get out of it is known as the time smooth velocity. So, that is the first difference between laminar flow and turbulent flow. In laminar flow, the velocity is a constant, but in turbulent flow the velocity can fluctuate. So, the instantaneous value measured at different points of time could have a different value. So, it is better always to express a time smooth velocity rather than an instantaneous velocity. So, what I have drawn over here, this Vz denoted by the black line is the oscillating velocity, whereas if you take a time smooth average, then the red line that I have drawn and denoted by V bar Z is the time smooth velocity. So, one can express the instantaneous velocity as the sum of the time smooth velocity and then a fluctuating component, whatever be this fluctuating component. The fluctuating component can be positive, the fluctuating component can be negative. So, the instantaneous velocity is a function of the time smooth velocity and the fluctuating component of the velocity. Now, if you look at the fluctuating component of the velocity, and if you decide to take a time average of the fluctuating component, then you can clearly see that this would be equal to 0. That means, at fluctuating component, when you take the average over a large time domain, then the fluctuating component will be 0. However, V prime Z square, if you take the time average of this is not going to be equal to 0. Okay. In fact, the fraction Vz square time smooth, the square root of this divided by Vz is known, it's essentially a measure of turbulence. So, the points which I am making over here is that the instantaneous velocity is the sum of the time smooth velocity and a fluctuating component of velocity. The fluctuating component of velocity, since it can be positive and negative, it can vary both, it can become both positive or negative. So, if you allow, if you find out the time smooth it over a large time domain, then V prime Z would be equal to 0. But V prime Z square, if you take the time smoothing of that, will not be equal to 0. So, sometimes the measure of turbulence is expressed as the square root of the time smooth velocity squared divided by the velocity divided by the time smooth velocity, and this is known as the measure of turbulence. But again, the point here is that the velocity fluctuates. The fluctuating part, when you take the time smooth, is equal to 0, but the square of that is not going to be equal to 0. So, now we move on to the Navier-Stokes equation, the equation of motion, where all velocities are expressed in terms of a time smooth velocity and a fluctuating velocity. This is written for the x component of Navier-Stokes equation. Similar to velocity, when we come to the pressure term, the pressure will also be in turbulent flow, the pressure will also have a time smooth component and a fluctuating component. So, the other terms are going to be del x of rho Vx times Vx like before, but the velocities are now expressed as the sum of time smooth and fluctuating. Similarly, for Vy time smooth fluctuating, this is the same. For Z also I can have the sum of time smooth and fluctuating, and the shear stress term will also have a time smooth and a fluctuating, and I have the normal body force. So there is nothing different, nothing unusual about this equation, except all velocity terms and the pressure term are expressed as a sum of a time smooth component and a fluctuating component. The same equation can, similar type of equation can also be written for the equation of continuity. What we do this at this point is we take a time smoothing of the entire Navier-Stokes equation. So if we take the time smoothing of this equation, then obviously this term would disappear, this term would disappear. Wherever I have v prime x alone, it will disappear, but here you would see you have a v prime x square, it will not, if your time smoothing of that would not be 0, and here for example you are going to have v prime x, v prime y, and if you take the time smoothing of that, it is not going to be equal to 0, whereas individually v prime x would be 0, time smoothing of that, v prime y, if you take the time average of this, it would be equal to 0. But the product of these two, when you take the time average of this, they may not be equal to 0. So when you take the time average of the entire equation, considering the facts that the products may not be equal to 0, but individually they are 0, then some of these terms will drop out, but some of these terms will remain as additional terms into the Navier-Stokes equation. And most of the additional transport of momentum that one would encounter in turbulent flow appears as a result of these fluctuating components of velocities. These fluctuations are characterized by the formation of eddies, and therefore these fluctuating components would give rise to additional stresses which are not visible, which are not important for the case of laminar flow, whereas we have a velocity which remains constant over time, but in turbulent flow it keeps on changing. So the products of these fluctuating components denote additional transport of momentum, unlike in laminar flow. So these explain the presence of these terms explains why the transport of momentum is more in the case of turbulent flow as compared to laminar flow. So when you take the time smooth of this equation, what you get is, as I mentioned, the left hand side would simply be this term, the pressure term would only have the time smoothing term, and these three terms, they are identical with the equation that you would get in laminar flow. This term is identical that you would get in laminar flow. The Gx, the body force term, would also be identical as in laminar flow. However, these three additional terms appear automatically in Navier-Stokes equation, which are products of the fluctuating components. Remember, I am writing it for the x component. So therefore v prime x appears in all three. The time smoothing of the product of these fluctuating components will not be 0, and collectively they are referred to as Reynolds stresses. And the Reynolds stresses, they are responsible for the additional transport, turbulent transport of momentum over and above that one would expect in the case of laminar flow. So up to this part, this is the laminar flow equation, and the three terms known as the Reynolds stresses, they essentially refer to the Reynolds stresses or the additional transport terms. So the next question is, we understand that in the case of laminar flow of a liquid through a pipe, we get a velocity profile. We know that the velocity profile is parabolic in nature, with a maximum in the velocity at the center line. We also have an idea of how would the velocity vary inside the boundary layer in laminar flow. But can there be an universal velocity profile which would explain, which would tell us about how the velocity varies in the case of a turbulent flow? Unfortunately, there is no such universal velocity profile which can be used from a point very close to the solid surface all the way up to the central line of flow when the flow is taking place in a pipe. Rather, it's customary to express velocity profiles in three distinct layers depending on which forces and which mechanism is important in those three layers. So, if you think of the layer which is very close to the solid surface, the effects of viscosity are important. So, this region where the effect of viscous forces are important, this region is termed as the viscous sublayer. So, in the viscous sublayer, the viscous forces are important, whereas if you go towards the core of the pipe, in that zone which is far from the pipe wall, the effect of viscosity would be negligible, and most of the momentum transport is going to be governed by the formation, exchange and transport of eddies. So, the momentum transport in the core region is controlled by the formation of eddies. So, that is the turbulent core region. So, you have a turbulent core region and a viscous sublayer very close to the wall, and in between the two, in between the viscous sublayer and the turbulent core, there exists another hypothetical layer which is known as the transition region, and in this region both the viscous forces and the turbulent transport of momentum both are going to be important. So, in a turbulent flow field, the velocity, the region, the flow region, the region, three regions, distinct regions are introduced: the viscous sublayer, the transition region and the turbulent core. And we have expressions for velocity in the viscous sublayer, in the transition region and in the turbulent core. Three distinct expressions of velocity, unlike in laminar flow where we just have one expression for velocity for the entire flow field. So, turbulent velocity profile is much more complicated than that of the laminar velocity profile. Additionally, the expressions of velocity in turbulent flow, be it in viscous sublayer or in turbulent core, they are obtained using a semi-empirical approach. So, the expressions are provided in the text, in the literature. These expressions are essentially averages of a huge amount of experimental data points. Okay. So, these are semi-empirical in nature, and they essentially denote averages over a large amount of experimental data, and their genesis is however semi-empirical in nature. The points to remember are, for three distinct regions we have three velocity profiles. The velocity profiles are obtained using a semi-empirical approach, and the demarcation of these three regions are also a result of experimental observations. So, I would simply provide you with the three velocity profiles just for the sake of completeness and to show how complicated turbulent flow is even for the case of flow in a pipe, and I will give you the expressions for the velocity profile in those three regions. The first is the turbulent velocity. First is the viscous sublayer, where Vz plus the velocity, axial component of velocity in dimensionless form, where this is V z by v star, this is the time smooth velocity, is equal to y v star by nu, the kinematic viscosity, and this v star is essentially root over tau w by rho. Root over tau w by rho has the same unit as that of velocity. So, this is used to non-dimensionalize the velocity, and it is called the friction velocity. And y v star by nu, again it is the non-dimensionless distance from the wall. So, it is denoted by y plus. So, for viscous sublayer where the viscous forces are important, the velocity profile would simply be equal to V z plus, which is by definition the time smooth axial velocity divided by friction velocity. This is the definition of friction velocity, is equal to a non-dimensional is equal to a dimensionless distance from the solid wall defined as y, distance from the wall, v star, the friction velocity, and the kinematic viscosity, and this is expressed as y plus. So, v z plus equal to y plus, and this is valid. The extent of the viscous sublayer is denoted by this. So, this is the expression for velocity in viscous sublayer. In transition region, the proposed profile is V z by V star, friction velocity again, that means which is equal to V z plus is 2.5 ln y V star by nu plus 5.0, where the region of applicability is 5 this. So, this expression which is obtained semi empirically, and the constants essentially denote are derived from a large experimental data set. So, they are averages over many experiments, and for the turbulent core the expression is V z plus is equal to 1 by 0.36 ln y plus plus 3.8, where y plus is greater than equal to 26. So, in other words, there is nothing called an universal velocity profile in turbulent flow. Okay. People have tried different means, different statistical techniques to obtain an expression for velocity profile in turbulent flow. However, the most common accepted way of treating turbulent velocity profile is to use 3 different zones and 3 different expressions for velocity that are obtained semi empirically, and the constants are essentially averages over a huge quantity of experimental data which are obtained. So, viscous sublayer, transition, and the turbulent core. And you are obviously can sense how difficult it is to express everything in terms of an universal velocity profile in turbulent flow. So, there is no such, it is so difficult to use an universal velocity profile. However, there is a velocity profile entirely empirical in nature, which is known as the 1/7 power law, that has been very successful in expressing the experimental results over a large domain of distance from the solid wall. So, here we have an expression of velocity as a function of distance from the solid wall, which is expressed, which is totally empirical in nature. But for some reason, this empirical velocity profile has been proven to be very successful in expressing the velocities over a large value of Reynolds number, and this is known as the 1/7 power law profile, which I am going to show now. The power law profile, the power law equation simply tells that Vz by u is equal to y by r to the power 1/7, where u is the centerline velocity, the r is the radius, the y is distance from the pipe wall. The region of applicability of this equation is if Reynolds number is within the range of 10 to the power 4 to 10 to the power 5. So, if Reynolds number is in this zone, it is entirely empirical in nature. So, this is empirical in nature. So, this would give us a profile Vz by u to be y by r to the power 1/7. This is also known as the 1/7 power law profile. And if you find out the average velocity, if you integrate it and you find the average velocity, this is 2n square by n plus 1 by 2n plus 1, where n in this case we have taken it to be equal to 1/7. So, for n equals 1 by 7, then V bar by u is equal to 0.8. Compare this with the case of laminar flow, where this constant is equal to 0.5. So, compared to a laminar velocity profile, the profile in turbulent flow is going to be flatter near the center. So, for the case of laminar flow, the velocity profile is parabolic in nature, and for the case of turbulent flow, it is going to be flat at the center. Higher the value of Reynolds number, the more turbulent it is, the length of this flat region, relatively flat region, where the velocity profile is not a function of r, will keep on increasing. So, in the extreme limit, when you have a very highly turbulent flow and the entire pipe can also can approach a velocity profile which is flat. Okay. So, you are going to go from a plug flow in the case of parabolic velocity distribution in the case of laminar flow to almost like a plug flow in the case of highly turbulent flow. So, this expression, the 1/7 power law, is extremely successful in fitting the experimental data with relatively high accuracy. However, there is one catch. The catch in this is that the 1/7 power law profile can fit the data points of the velocity very well when the distance from the solid wall solid wall is slightly higher. In other words, this profile fails when you approach the solid wall. So, the 1/7 power law, though successful in expressing the velocity with sufficient accuracy, it cannot track the profile when you approach the solid wall. In fact, when the value of y by r, that is the distance from the solid wall non-dimensionalized by the radius, is less than 0.04, it gives you can work it out infinite velocity gradient at the wall. Which is not possible. You cannot have an infinite velocity profile at the wall. So, the region of applicability of this 1/7 power law equation is definitely not near the wall. So, therefore, one must re-emphasize that although the profile fits the data close to the center line, it fails to give a zero slope at the center line. That is the first problem, and the second problem is that it gives an infinite velocity gradient at the wall. So, infinite gradient at the wall and does not give zero slope at the center line. Of these two, this is going to create the maximum problem if we try to use this expression for the wall for the use of the momentum integral equation, because the momentum integral equation, if you recollect, is simply tau w by rho is equal to u square d del dx, and then over here integration of u by u 1 minus u by u times d eta. Eta varies from 0 to 1. So, if you take the simplest possible form of the momentum integral equation, on the left hand side I have tau w, on the right hand side I have a velocity profile, and here I have a very handy power law equation which can be used here in order to express it as u by u to be equal to eta to the power 1 by 7, or I can express it over, I can plug it in here in order to obtain the expression for tau w. If you look at these two sides, it becomes apparent that you may be able to use 1/7 power law on the right hand side, since you are integrating the expression over the entire flow regime. That is, you are integrating from 0 to 1 over d eta. So, whenever you integrate an expression that contains some experimental error, the error gets minimized, the error gets reduced. But what happens in tau w? In tau w, you have to express tau w in terms of velocity gradient. That means you are differentiating the velocity profile. The moment you differentiate a data containing error, you magnify the error. So, power law equation, since it fails and it gives infinite velocity gradient at the wall, and the velocity gradient at the wall is connected with the shear stress at the wall. So, power law equation in this form cannot be used with the left hand side of the momentum integral equation where we have tau w. On the other hand, the right hand side essentially denotes an integration over the velocity profile. So, power law 1/7 power law is an ideal candidate to be used on the right hand side of the momentum integral equation. So, when we try to plug in a universal velocity profile on the left hand side of the momentum integral equation, the problem we see is that there is no such thing as an universal velocity profile. At the best, we have 3 velocity profiles in 3 regions, which makes it difficult, cumbersome to be used with the momentum integral equation. And the whole purpose of momentum integral equation is to simplify the entire process. So, we cannot use those 3 profiles. Now, we have a 1/7 power law profile which fits the data rather well near the center line, but it doesn't do it so good a job near the pipe wall. So we can use it on the right hand side of the momentum integral equation where we integrate the profile. The left hand side of the momentum integral equation contains wall shear stress, and wall shear stress is generally expressed in terms of velocity gradient at y equals 0. And we know that 1/7 power law fails measurably when y approaches 0. It predicts an infinite gradient which is impossible, which is physically indefensible, and therefore 1/7 power law cannot be directly used to evaluate the wall shear stress and therefore the left hand side of the momentum integral equation. So in order to use momentum integral equation for turbulent flow, we will use 1/7 power law for the right hand side, but we cannot use 1/7 power law for the left hand side, and we have to devise something else. So that's what we will discuss in the next class.